The United States Merchant Marine Academy's Science and Innovation Club would like to welcome you to the 2021 National Chemistry Week virtual demonstration. For this year's theme, Fast or Slow, What Makes Chemistry Go, we have prepared two different experiments to highlight the wonders of fast and slow reactions to chemistry. Oxidation, will it rust? And the colors of combustion. Since we are America's premier institution for preparing future merchant marine officers, we will explain how this relates to the maritime industry. We hope you enjoy.
Good morning, or good afternoon, or good evening, or good night, wherever you might be. I'm an important midshipman at the United States Merchant Marine Academy. Do you know why? Because I love science so much that I am in the science club. My name is Midshipman Michael DeLesner, and I'm here to show you the magic and the extreme practicality of science. Let's get to the experiment.
USMMA, my school, is in charge of training the future officers of the Merchant Marine. Now, we're not Marines like the military. We're the people who get on ships and safely navigate them through the ocean from port to port. These ships are the size of skyscrapers in New York, if you laid them on their side. These ships are made from steel, and steel and salt water, like the ocean, do not like each other. So to protect the hull and the propeller from saltwater rust, we need the help of zinc anodes. The zinc takes the hit for the steel and rust before the steel does. To supplement this, the extra special USMMA Science Club will use iron nails to represent the steel hull and propeller. We will be testing how different metals protect the nails from rusting to see if zinc is the best protector from the sea.
Here is the list of the materials that we used to conduct this insane, mind-breaking experiment. Water, 200 milliliters, nails made of iron, copper, magnesium, a little bit of zinc, and a lot of zinc. Here are the ranked oxidation potentials for magnesium, zinc, iron, copper, and dissolved oxygen in the water.
If all these metals and water are present, the dissolved oxygen in the water, which has the lowest oxidation potential, will undergo a reaction called reduction, starting to receive the electrons, rather than losing the electrons shown here. Zinc and magnesium have a higher oxidation potential than the iron and the copper alloys in the ship propeller. They're more inclined than the propeller's metal to lose and provide electrons to the dissolved oxygen in the water, a process known as oxidation. In the electrochemical cell, the electrode where oxidation occurs is called the anode. If the zinc or magnesium is connected to the iron or steel, it is called a sacrificial anode. This means they are being intended to protect the metal from being oxidized or rusting.
As seen here, the magnesium has a high oxidation potential, so it serves the same role as zinc in protecting the metal. As you can see here, the metal is hardly even covered in rust. The copper, however, has a lower oxidation potential than iron, so it encourages the iron to lose more electrons, causing it to rust at a quicker rate, possibly accelerating the rusting process surrounding it. As shown here, the zinc oxide and the magnesium oxide precipitate effects on the iron nail causes the iron sample to appear like this.
Here is a side-by-side comparison of all of our rusting results. As you can see here, the results directly coincide with what we predicted.
Hey there kiddos, I'm Nate. I investigated various combinations of chemicals and their effects of rusting on an iron nail, as shown with these test tubes.
The following materials were used: phosphoric acid, sodium phosphate monobasic, sodium phosphate dibasic, and sodium phosphate tribasic. The glassware used was beakers, graduated cylinders, pipettes, and test tubes. While Superfund materials were used, safety was observed throughout this experiment. We wore eye goggles and were very careful handling the chemicals. We did not drink any of the chemicals.
When we sail across the huge oceans, our ships get yucky and rust. Steel oxides in air are what causes this to happen, which is a reason of why we paint the boats, because that helps delay the rusting process. In this experiment, we created 3 mixtures and 1 control, and then poured these mixtures into the test tube shown before you, sticking an iron nail inside. The control mixture was simply water. The other 3 mixtures were phosphoric acid and monosodium phosphate, first mixture, monosodium phosphate and disodium phosphate, the second mixture, and disodium phosphate and trisodium phosphate, the third mixture. Each test tube was left slightly ajar to allow air inside to initiate the rusting process. Our prediction for this experiment is that the most basic solution, the one with the least amount of H+ ions, will rust the nail the least, and the one with the most acidic solution, the one with the most H+ ions, will rust the iron nail the most. Success! Mixture number 3 caused the nail to become almost preserved, especially when compared to our control nail. This is because in a basic solution, reduced hydrogen ions shift second half reaction to the left, inhibiting dissolved oxygen in water to receive these electrons. Since the dissolved oxygen can take in electrons, the iron nail can't lose any. As a result, the iron does not oxidize. This is why no rust nor iron precipitates are formed. Thanks to the buffer components, the pH is well maintained and iron is well protected for a long time. This chemical system is used in ship boiler water to prevent boiler corrosion in the pipes. By maintaining a stable pH in the boiler water, we prevent the formation of iron precipitates and rust, which can be harmful to both the pipes themselves by corroding away at them, as well as the machinery, which will have to deal with that rust in the boiler water. Additionally, without an electron receiver such as O2 in the water, iron will not rust. This is why on steamships they do such things as remove the oxygen from the boiler water.
Here is a side-by-side comparison of all of our rusting results. As you can see here, the results directly coincide with what we predicted.
Hello friends, Uncle Drew here. In my experiment, I utilized acid, base, and neutral chemical solutions to investigate how the respective pH affects the rusting process on an iron nail.
For this experiment, the following materials were used: 8 milliliters of hydrochloric acid solution, 8 milliliters of neutral water, 3 milliliters of sodium hydroxide basic solution, and 5 milliliters of neutral water mixture, 8 milliliters of control water, and 4 test tubes, and 3 iron nails.
This experiment is very applicable to the maritime industry because it allows one to observe how a solution's pH can affect the corrosion and rusting of a material. Merchant vessels are located all over the 7 seas. Some even cross different bodies of water. In summary, a ship can experience many different pH levels during its voyage. Understanding how pH affects the material's rusting will greatly assist in the type of material a vessel should use. After analyzing the data obtained from the performed experiment, it can be concluded that a more acidic solution will accelerate the rusting process. In other words, the lower the pH, the more the material is prone to rusting. The reasons are the same as present in the buffer experiment. For example, an acidic solution with high amounts of hydrogen ions will shift half of the equation to the right, promoting iron oxidation, thus rusting. And a basic solution with low amounts of hydrogen ions will shift all half reactions to the left, inhibiting iron oxidation, thus rusting. Unlike buffered water, the basic solution does get weaker over time due to the dissolved carbon dioxide, so rusting will occur. As we've seen a bit here, when the solution becomes less base. Although basic solutions prevent rusting, it may cause metal embrittlement if it's too base, so it should be avoided at all costs.
It's a side-by-side comparison of all our rusting results. As you can see here, the results directly coincide with what we predicted.
What's up guys, my name is Midshipman Mike Aguilar, and today we're doing an experiment with rusting. And for this experiment, we're going to be changing the surrounding temperatures. For each of these samples, we are using deionized water. In this experiment, we are using 3 nails, 3 test tubes, and 3 samples, each of them containing 8 milliliters of water, where we're going to put 1 in the fridge, 1 in the oven, and 2 at room temperature. For the sample that we put in the fridge, we've set the fridge to be 5 degrees Celsius. This is very cold, just like when a ship's heading to Antarctica. The coldness slowed down the rusting process in comparison to the room temperature one. This is like the same as if it was in the Long Island Sound. Lastly, the hottest sample we used caused the iron nail to rust the fastest. This rusting was the same that occurs on the ship that sailed in the movie The Pirates of the Caribbean. Arrgh! Why does this happen? Well, I'll tell you what. Basically, higher temperatures lead to faster reactions by speeding up. Since the dissolved oxygen had a lower oxidation potential, it will serve to receive the electrons and undergo a reaction called reduction. And iron having a higher oxygen potential will provide electrons to dissolve oxygen in the water, called a reaction, oxidation.
Here is a side-by-side comparison of all of our Rustin results. As you can see here, the results directly coincide with what we predicted.
Thank you for listening to our talk about rusting.
Now, be ready for explosive reactions.
Hi, my name is Ethan Giravata.
I'm Anthony Suarez.
And I'm Nathaniel Schmidt.
And we are midshipmen at the United States Merchant Marine Academy. Today, we will be demonstrating the chemistry behind the different flares we use during times of distress while on a ship at sea. These combustions are not your normal explosions, like when you drink coffee in the morning or drink prune juice. These are flares. The orange flare is a signal to other people for times of distress while at sea. First, we will go through the materials we need to do this. The materials we need are proper PPE, a spatula, 2 ceramic bowls, 3 grams of calcium nitrate, 3 grams of barium, 2 grams of sugar, 1 drop of concentrated sulfuric acid, and a pipette to drop the sulfuric acid. We will mix the calcium nitrate, barium, and sugar in the ceramic bowl thoroughly while we put a small divot on the top of the mixture. We will then drop 1 drop of the concentrated sulfuric acid on top of the mixture and step back as the mixture starts to combust. This happens when the calcium nitrate decomposes the organic substances very rapidly when mixing the sulfuric acid in the mixture, which shows the combustion and inflammation.
When you want to party on a ship, you would use the purple flares. This flare uses potassium chlorate instead of calcium nitrate.
We are using the same materials as the last experiment, but we will instead replace the 3 grams of calcium nitrate with 3 grams of potassium chlorate. The other materials are as shown.
The combustion that occurs is a more purple flare compared to the other orange flare. Again, this happens when the potassium chlorate decomposes the organic substances very rapidly when mixing the sulfuric acid in the mixture, which shows the combustion and inflammation.
If you want to get a little spooky for this upcoming Halloween, you can use a green flare. This flare uses barium chloride instead of the other 2 compounds. The materials are also the same as the past 2 experiments, but we are changing the reactant agent with barium chloride to get that green color. The combustion is a more greenish flare as seen in the video compared to the orange and purple flares. This happens when the barium chloride decomposes the organic substances very rapidly when mixing the sulfuric acid in the mixture. This shows the combustion and inflammation.
This combustion occurs when the electrons in the metal atoms in these compounds get excited upon being heated up. The excited electrons are unstable. Upon their return back to their stable ground states, excess amounts of energy are released in the forms of lights of different colors due to their different electronic structures. While traveling the 7 oceans on a ship, the ship will corrode in the water over time, which then damages it even more. The water will cause the oxygen to combine with the metal to lose its electrons and therefore rust. Because of this, zinc sacrificial anodes are placed on the ship's hull. Zinc is a highly active metal that has a higher oxidation potential than the metal used on the ships. These are then placed on the hull to protect the ship through anode cathodic protection. This is when the zinc is electrified to transfer the oxidation to the zinc instead of the structure. In cases of emergency, distress flares are used to signal any other nearby ships or the U.S. Coast Guard that we are in danger so they can come to the rescue. The red flare is used during the daytime and nighttime, while the orange flare can only be used during the daytime. These are very dangerous, so please do not try this at home.
Happy United States Merchant Marine Academy.
Happy